On September 13, 2024, an automated sky survey telescope in Chile registers a faint point of light moving against the stellar background. The computer flags it. The coordinates are logged. Within hours, astronomers across 3 continents turn their instruments toward the same patch of sky, and the light is still there, still moving, still faint. They measure its velocity, they calculate its trajectory, and they realize, with the quiet thrill that accompanies such discoveries, that this object is not bound to the sun. It arrives from somewhere else entirely. The designation comes quickly, 3I Atlas. The third confirmed interstellar object ever detected passing through our solar system. Only took humanity 4.5 billion years to spot 3 of them. The I stands for interstellar, a category so new it barely existed before 2017. The Atlas refers to the survey system that found it, a network of robotic telescopes scanning for anything that moves or changes or explodes in the night. This one does none of those things dramatically. It simply crosses through, obeying laws of motion older than planets, carrying itself on a path determined long before Earth had oceans. The light it reflects is ancient sunlight. Photons that left our star 8 hours ago, bounced off rock and ice tumbling through the outer solar system, and arrived at a sensor in the Atacama Desert. The object itself is perhaps 400 million kilometers away when first detected, roughly the distance between the Sun and the asteroid belt, though it passes nowhere near the belt itself. Its orbit is hyperbolic. This is the technical term for a trajectory that does not close, that does not return, that enters the Sun's gravitational influence and then escapes it entirely. A one-time visitor with no plans to stay. Astronomers begin the patient work of observation. They schedule telescope time. They compile photometry data, measuring how the object's brightness changes over hours and days. They attempt spectroscopy, trying to split its faint reflected light into component wavelengths, searching for the fingerprints of molecules on its surface. The object is dim. It reflects very little light. To see it at all requires instruments of extraordinary sensitivity. Cameras cooled to nearly absolute zero to reduce thermal noise. Mirrors polished to within a few atoms of perfection. Even then, 3 Atlas appears as little more than a smudge, a faint statistical signal extracted from the cosmic background. But the data accumulates. The object is moving at approximately 32 kilometers per second relative to the Sun, far faster than any asteroid or comet native to our system could achieve without a gravitational assist. Its trajectory angles inward from the direction of the constellation Lyra, though of course it did not originate there. Lyra is simply the part of the sky it happened to pass through on its way here. Tracing the path backward, astronomers estimate it has been travelling through interstellar space for millions of years, possibly tens of millions, a silent crossing of the space between stellar neighbourhoods. There is something unusual in the brightness measurements. The light reflected from 3I Atlas varies in a regular pattern, brightening and dimming over a period of approximately 16 hours. This periodicity suggests rotation, the object tumbling end over end as it travels, presenting different cross-sections to the Sun and, by extension, to telescopes on Earth. But the amplitude of the variation is large, far larger than a sphere or even a moderately elongated ellipsoid would produce. The light curve implies something shaped more like a shard, a splinter, a fragment. Only took 3 interstellar objects to find one this strange. The first, one Oumuamua, passed through in 2017, also elongated, also mysterious, also gone before detailed study could be completed. The second, 2I Borisov, arrived in 2019 and behaved like a comet, outgassing and forming a small coma, familiar and almost comforting in its normalcy. Now comes 3I Atlas, neither entirely comet-like nor entirely inert, something in between, something that resists easy categorization. The mystery is its shape. That much is clear from the start, but shapes in space are determined by forces gravity, collision, rotation, heat, pressure, and each force leaves a signature. The work now is to read those signatures, to reconstruct the object's history from the way it tumbles through the dark. Somewhere in the data is a story written in density and albedo and rotational dynamics, a story that begins in another star's planetary system, in conditions no human has ever observed directly, under physical laws that are universal, but whose outcomes remain strange and varied and surprising. The telescopes track it night after night. The light fades slowly as the object moves farther from the sun, heading outward toward the heliopause and beyond. There is no urgency in its motion, no drama. It simply continues, as it has continued for longer than human civilization has existed, carrying its strange shape and unknown composition back into the interstellar medium. The work of understanding it has only just begun. The trajectory of 3i Atlas extends backward through time and space like a thread pulled taut across the galaxy. Astronomers plot its path using precise astrometric measurements, comparing its position against background stars over successive nights, calculating velocity vectors in 3 dimensions. The math is elegant and unforgiving. Given the object's current position and velocity, given the gravitational influence of the sun and planets, the equations trace its route in reverse, unwinding the path it has travelled to reach this moment. The calculations suggest an origin somewhere in the galactic disk, that vast flat spiral of stars and gas clouds rotating around the Milky Way's central bulge. Not from any specific star system that can be identified, the uncertainties are too large, the distances too great, the possible sources too numerous, but the direction is clear enough. 3i Atlas approached from the general direction of the Orion Arm, the same spiral structure that contains our Sun, entering the solar system from above the ecliptic plane at a modest angle, passing through regions where few planets orbit, where space is comparatively empty. How long has it been travelling? The speed provides a minimum estimate. At 32 kilometers per second through interstellar space, covering the distance between neighbouring star systems, typically 4 to 6 light-years, would require hundreds of thousands of years at least. But neighbouring systems are rare. Most of the galaxy is emptiness, vast expanses where stars are separated by dozens or hundreds of light-years. If 3i Atlas originated from a system 20 light-years away, it has been in transit for nearly 200,000 years. If it came from 50 light-years distant, the journey spans 500,000 years. If farther still, the timescales extend into millions of years, into durations that dwarf human history, that predate the emergence of modern Homo sapiens. During that crossing, the object experienced conditions unlike anything found in the inner solar system. The temperature of interstellar space hovers around 3 Kelvin, barely above absolute zero, cold enough to freeze any remaining volatiles into solid ice, cold enough to make rock as brittle as glass. Cosmic rays bombarded the surface continuously, high-energy particles from distant supernovae and active galactic nuclei, gradually altering the chemical composition of surface materials, breaking molecular bonds, creating new compounds that exist only in deep space. Interstellar dust grains, each smaller than a bacterium, impacted the surface at high velocity, sandblasting the leading-edge atom by atom over millennia. The object would have passed through regions of varying density in the interstellar medium. Some volumes of space contain only a few atoms per cubic centimetre, mostly hydrogen, tenuous beyond any vacuum achievable in terrestrial laboratories. Other regions are denser, molecular clouds where star formation occurs, though even these dense clouds remain emptier than the best vacuum chambers on Earth. If 3i Atlas traversed such a cloud, it would have encountered slightly higher rates of dust impacts, slightly more frequent collisions with gas molecules. Though the overall effect remains negligible, space is patient and space is vast, and erosion on these scales proceeds immeasurably slowly. Only took a few million years to cross a neighbourhood. The galaxy itself rotates with the stately indifference of all large gravitational systems, completing one full rotation every 230 million years or so. During 3i Atlas's journey, the stellar configurations it passed through would have shifted slightly. Stars moving in their own orbits around the galactic centre, some approaching each other, others drifting apart. The constellations that humans see from Earth are temporary arrangements, patterns that dissolve over millions of years as individual stars follow their gravitational destinies. 3i Atlas witnessed none of this consciously, of course, being merely stone and ice and perhaps metal, but it moved through these changing configurations, passing near stars whose light might one day reach Earth, or might never reach anywhere inhabited at all. There is a certain irony in tracing paths backward through space. The farther back the calculations extend, the less certain they become. Small uncertainties in the object's current position and velocity compound over time, creating an expanding cone of possible origin points that eventually encompasses thousands of star systems, then millions, then entire sectors of the galactic arm. Astronomers speak of solution spaces and probability distributions, acknowledging that the true origin of 3i Atlas may never be known with certainty. The object carries no label, no signature isotope ratios unique to a particular stellar nursery. No way to definitively identify which planetary system expelled it into the interstellar void. What can be said is that somewhere, orbiting some star, conditions existed that allowed this object to form and then to leave. Perhaps it condensed in the outer reaches of a planetary system, in the equivalent of that system's Kuiper belt or Oort cloud, where icy bodies accumulate beyond the orbits of major planets. Perhaps it formed closer in, and was later ejected by gravitational interactions with a giant planet, flung outward in a process that happens routinely in young solar systems still sorting themselves gravitationally. Perhaps it was part of a binary system where the companion star's gravity perturbed orbits chaotically, or perhaps it formed during the system's initial collapse from a molecular cloud and never settled into a stable orbit at all. The ejection event itself would have been undramatic from the object's perspective. No explosion, no catastrophic collision, just a gradual acceleration as it swung past a massive planet or star, gaining velocity through gravitational interaction, reaching escape velocity and continuing outward. One moment bound to its home star, the next moment free. The transition marked only by the subtle shift from elliptical to hyperbolic trajectory. The object would have continued tumbling as it had always tumbled, reflecting starlight as it had always reflected starlight, aware of nothing, changed in no meaningful way except in the fundamental reorientation of its future, no longer a member of any planetary system, now a wanderer, now something that belongs to the galaxy itself rather than to any particular star. Only took one close encounter to become an exile. The universe is full of such accidents. Such random gravitational interactions that send small bodies careening into interstellar space. Current estimates suggest billions of such objects drift between the stars in our galaxy alone. A vast population of cosmic debris, fragments of planetary systems scattered across light years, invisible unless they happen to pass close to a star with astronomers watching. 3i Atlas is remarkable only in that it was detected. Only in that it crossed paths with one of the few star systems capable of noticing its passage. Most interstellar objects complete their journeys unseen, unmarked, unknown, and now it moves through our solar system, the sun's gravity bending its path slightly, pulling it inward and then releasing it. A brief interaction that will alter the object's trajectory by a few degrees, a change that might, millions of years hence, determine whether it passes close to another star or misses it entirely. The scales are enormous, the forces are subtle, the outcome remains uncertain, the object continues regardless. The comparison begins almost immediately. As soon as astronomers confirm that 3i Atlas follows a hyperbolic trajectory, the question arises, how does it compare to the others? Only 2 previous interstellar objects have been detected passing through our solar system, and each arrival rewrote assumptions about what such objects might be like. The sample size remains absurdly small, 3 objects observed out of billions that likely exist, but patterns emerge even from tiny samples. And the differences between these 3 visitors prove as instructive as any similarities. Oumuamua arrived first. In October 2017, detected by the Pan-STARRS telescope in Hawaii, it moved fast, more than 26 kilometers per second relative to the Sun, on a trajectory that brought it unusually close to the inner solar system, passing within 23 million kilometers of Earth. Its shape dominated the early analysis. Light curve measurements suggested an elongation ratio of at least 10 to 1, possibly more, making it either cigar-shaped or perhaps pancake-shaped, depending on how the rotation axis aligned with Earth's line of sight. No coma was detected, no outgassing, no cometary activity despite passing well within the orbit of Mercury, where sunlight should have vaporized surface ices. Yet it exhibited a slight non-gravitational acceleration as it departed the solar system, a tiny push that could not be explained by solar radiation pressure alone if the object were rocky. The mystery remained unsolved. Oumuamua faded from view before detailed spectroscopy could be completed, leaving behind more questions than answers. Tui Borisov arrived in August 2019, detected by amateur astronomer Gennady Borisov using a telescope he built himself. It behaved like a comet, comfortingly normal in most respects. As it approached the Sun, surface ices sublimated, creating a visible coma of gas and dust, a tail extending millions of kilometers behind it. Spectroscopic analysis detected water vapor, carbon monoxide, and other volatiles consistent with comets from our own Oort cloud. Its nucleus appeared more spherical than Oumuamua, with an elongation ratio closer to 2 to 1. The orbit was hyperbolic but less extreme, suggesting it had been travelling through space at a more leisurely pace, perhaps 15 kilometers per second through the interstellar medium. It provided reassurance that not all interstellar objects were strange, that some planetary systems produced objects recognizably similar to those formed around our Sun. Now 3I Atlas arrives, and it fits neither pattern precisely. Its velocity falls between the other two 32 kilometers per second, faster than Borisov, slower than Oumuamua. Its trajectory brings it nowhere near Earth, passing through the outer solar system at a comfortable distance. More than 600 million kilometers at closest approach to the Sun, well beyond Mars, in regions where sunlight dims and surface temperatures remain perpetually frigid. Early observations detect no coma, no obvious outgassing, suggesting either a composition lacking volatiles or surface temperatures too cold for sublimation to occur. Yet the spectral signature differs from Oumuamua's. The reflected light shows hints of ice absorption features, subtle bands in the infrared spectrum that might indicate water ice, or carbon dioxide ice on the surface, though the signal-to-noise ratio makes definitive identification difficult. The shape sets it apart most clearly. While Oumuamua's light curve suggested extreme elongation and Borisov's suggested moderate elongation, 3 Atlas exhibits a light curve amplitude implying something in between but with irregular variations superimposed on the primary rotational period. The brightness does not vary smoothly as a simple ellipsoid would. Instead, the curve shows secondary bumps and dips, asymmetries that hint at a more complex geometry, perhaps a bifurcated shape. 2 lobes connected by a narrow neck, or perhaps a single elongated body with large impact craters or missing chunks. Surface features that create brightness variations as different facets catch sunlight. Only took 3 visitors to establish that interstellar objects come in varieties. The temptation exists to generalize from this tiny sample, to construct theories about what interstellar space contains based on 3 data points. But astronomers resist such temptation. Mostly, each object arrived from a different direction, presumably from a different origin system, formed under different conditions, ejected by different mechanisms, that they share little beyond their hyperbolic orbits, and their status as visitors should surprise no one. The galaxy contains multitudes. Planetary systems form in diverse environments around stars of different masses, different metallicities, different ages, in regions with different dust densities, different radiation fields, different gravitational perturbations from nearby stars. The objects these systia produce and then lose reflect that diversity. The spectral differences particularly intrigue researchers. Oumuamua appeared reddish in colour, suggesting an old, radiation-weathered surface rich in organic compounds or metallic minerals. Borisov appeared neutral to slightly blue, consistent with fresh ice exposed by outgassing. 3-Psi Atlas shows a spectrum that suggests surface ice but without active sublimation. A frozen comet, perhaps. Or an object that lost its volatiles long ago, except for a thin frost layer deposited during its passage through an interstellar molecular cloud. The albedo, the fraction of light reflected versus absorbed, appears higher than Oumuamua's, but lower than fresh ice would suggest, indicating a surface partially darkened by radiation or dust accumulation. There exists a quiet mystery in the rotation rates as well. Oumuamua rotated with a period of approximately 8 hours, tumbling rapidly, suggesting either a small object or one with an unusual mass distribution. Borisov's rotation period was harder to determine due to the coma obscuring the nucleus, but estimates suggested something closer to 24 hours. 3 Atlas rotates with a 16-hour period. Intermediate again, neither fast nor slow by the standards of small solar system bodies. The tumbling appears stable. The rotation axis fixed in space rather than precessing chaotically, suggesting the object is not a loose rubble pile but has enough structural integrity to maintain its angular momentum over millions of years. The non-gravitational acceleration that puzzled Oumuamua researchers does not appear in 3I Atlas's trajectory, at least not yet, not within the precision of current measurements. The object follows the path predicted by gravity alone, a hyperbolic Keplerian orbit modified slightly by the gravitational influence of Jupiter and Saturn as it passes through their distant neighbourhoods. This simplifies the analysis considerably. No need to invoke exotic explanations. No mysterious rocket effect pushing it along. Just an inert body obeying Newton's laws, falling toward the sun and then climbing back out of the gravity well, losing speed as it rises, eventually returning to roughly the velocity it possessed when it entered, headed back into the dark. Only took a few months to gather most of the data that will ever be gathered. 3I Atlas is fading now as it moves farther from the sun and farther from Earth, the geometry becoming increasingly unfavourable for observation. Soon it will be too dim for all but the largest telescopes, and then too dim for any telescope. The window of opportunity closes quickly for interstellar objects. They appear, they pass through, they vanish, usually within weeks or months of detection. What has not been measured by then will likely never be measured. The archive of observations grows slowly, each image adding fractionally to humanity's understanding, each spectrum a small piece of a puzzle whose full picture may take decades or centuries to assemble, requiring hundreds or thousands of interstellar visitors before statistical patterns emerge clearly. The shape problem emerges not as a dramatic revelation, but as a gradual accumulation of puzzling data points. Astronomers measuring the brightness of 3I Atlas over successive nights notice the pattern. Immediately, the object brightens and dims in a regular cycle, completing one full oscillation every 16 hours and 13 minutes. This periodicity itself is unremarkable. Most asteroids and comets rotate, and rotation causes brightness variations as different surface areas reflect sunlight toward Earth. A spherical object rotating shows no brightness change at all. An ellipsoidal object shows modest variations, perhaps 20 or 30% difference between maximum and minimum brightness. But 3I Atlas shows brightness variations exceeding a factor of 3, meaning the object appears more than 3 times brighter at maximum than at minimum. The implications are straightforward. For such large amplitude variations to occur, the object must present dramatically different cross-sectional areas to observers as it rotates. Either it is extremely elongated, shaped like a needle or a rod, or it has a highly irregular profile, perhaps fragmented or bifurcated, with large protrusions or deep cavities that catch or shadow sunlight depending on orientation. The light curve itself provides clues. Photometric measurements plotted over time create a characteristic double-peaked pattern, with 2 maxima and 2 minima per rotation period, suggesting the object shows its broadest profile twice per rotation and its narrowest profile twice per rotation, consistent with an elongated body tumbling end over end. But the peaks are not identical. The 2 brightness maxima differ slightly in height, and the 2 minima differ slightly in depth, asymmetries that indicate the object is not a simple ellipsoid, but something more complex. Perhaps one end is larger than the other, or perhaps the surface reflectivity varies across different regions, darker areas absorbing more light, brighter areas reflecting more, or perhaps the shape itself is genuinely irregular, neither ellipsoidal nor cylindrical but fractured, angular, a shard rather than a smooth form. Only took a few dozen measurements to recognize the problem. The question then becomes what shapes are possible. Astronomers construct models, simulating how different geometries would produce brightness variations matching the observed light curve. They try elongated ellipsoids with various axis ratios 3:1, 4:1, 6:1, adjusting the rotation axis orientation and the surface albedo distribution, searching for configurations that reproduce the observed pattern. Some models fit reasonably well, others fail to match the asymmetries. The best fit suggest an elongation ratio of at least 4:1, possibly higher, making 3 Atlas longer than it is wide by a factor of 4 or more. For comparison, most asteroids observed in our solar system have elongation ratios below 2:1. A few reach 3:1, typically small fragments from catastrophic collisions, shards of larger bodies smashed apart by impacts. Ratios of 4:1 or higher are rare, confined mostly to contact binaries, 2 separate bodies orbiting so closely they touch, creating a dumbbell or peanut shape, or to rubble piles barely held together by their own weak gravity. Loose aggregations of smaller fragments that have not yet collapsed into spherical forms. The fact that 3I Atlas maintains such an elongated shape while tumbling stably through interstellar space for millions of years suggests it possesses structural integrity, some internal strength beyond mere gravitational cohesion. The size remains uncertain. Brightness alone does not reveal size without knowing albedo, how reflective the surface is. A large dark object and a small bright object can appear equally bright from Earth. Astronomers estimate the albedo based on spectral characteristics and comparison with similar objects, but the uncertainty is large. If the surface reflects 30% of incident sunlight, similar to dirty ice or weathered rock, then 3I Atlas measures perhaps 600 meters along its long axis, maybe 200 meters across its narrow width. If the surface is darker, reflecting only 10%, then the object could be twice as large, more than a kilometer long. If brighter, it could be smaller. The range of possibilities spans an order of magnitude. What forces create such shapes in our solar system? Elongated asteroids typically form through collisions. A larger body breaks apart, and fragments inherit irregular geometries determined by fracture patterns in the parent body. Impact physics governs the process. Stress waves propagating through rock, tensile and compressive forces exceeding material strength, cracks forming along planes of weakness. The resulting fragments are angular, asymmetric, covered in impact scars and fresh fractures. Over time, subsequent smaller impacts gradually erode sharp edges, chipping away protrusions, filling in cavities with ejecta, a slow sand-blasting process that operates over billions of years but never entirely smooths away the original irregular form. Alternatively, elongated shapes can arise from rotational stress. If a rubble pile spins too quickly, centrifugal forces overcome the weak self-gravity holding the components together, and the object begins to stretch, material migrating toward the equator, creating a flattened or elongated profile. Spin faster still, and the object can break apart entirely, fissioning into 2 or more separate bodies. But 3I Atlas rotates relatively slowly. 16 hours is leisurely by asteroid standards. far too slow for rotational stress to matter. Whatever shaped this object, rotation was not the primary sculptor. Only took one collision, perhaps, to create this form. Or perhaps many collisions over millions of years, each impact chipping away material, each close encounter with a planet or moon deforming the structure slightly through tidal forces. The object carries its history in its geometry, but reading that history requires knowing what the object is made of, how strong its materials are, what temperatures and pressures it has endured. Without a spacecraft visiting 3i Atlas, without surface samples or seismic measurements or detailed imaging, these questions remain open, answered only tentatively through remote observations that capture a few photons reflected from a surface no human eye will ever see directly. The tumbling itself provides information. The fact that 3i Atlas rotates with a stable period, not speeding up or slowing down noticeably, suggests it is in a low-energy rotational state, what dynamicists call principal axis rotation. The object spins around its axis of maximum moment of inertia, the configuration that minimizes rotational energy for a given angular momentum. Objects in excited rotational states tumble chaotically, their rotation axes precessing and wobbling, dissipating energy as internal friction gradually damps the motion. That 3i Atlas appears stable suggests either it has been tumbling long enough for such damping to complete, or it never experienced the violent events that would excite complex rotation in the first place. The shape problem remains unsolved. The light curve constrains possibilities but does not uniquely determine geometry. Multiple shapes can produce similar brightness variations. What astronomers have are constraints lower bounds on elongation, upper bounds on size, estimates of surface properties but not certainty. Not the kind of definitive answer that comes from close-range imaging or physical samples. The object will keep its secrets mostly intact, revealing only what can be gleaned from the faint light it reflects during its brief passage through observable space. The tumbling reveals itself in subtle patterns of light. As 3i Atlas rotates, different surfaces catch sunlight at different angles, and the intensity of reflected light varies accordingly. Astronomers measure this brightness dozens of times per night, building up a detailed light curve that maps the object's appearance through one complete rotation and then another and another, searching for regularities, for deviations, for anything that might constrain the geometry or surface properties of this distant visitor. The rotation period settles at 16 hours, 13 minutes, and approximately 40 seconds, though the precision of that final measurement remains limited by the faintness of the object and the spacing of observations. This period appears constant across multiple nights of observation. No detectable spin-up or spin-down, no gradual change that would indicate torques acting on the object. In principle, outgassing from sublimating ice could produce such torques, jets of vapour erupting from sun-facing surfaces, acting like tiny rocket engines that alter rotation rates over days or weeks. But 3 Atlas shows no evidence of outgassing, no coma, no jets, and its rotation remains steady, locked into whatever spin state it possessed when it entered the solar system. The tumbling is end over end rather than spinning like a top. The distinction matters. An object can rotate in different ways depending on its shape and which axis it spins around. A football thrown with a spiral rotates around its long axis, presenting the same profile continuously. A football tumbling end over end rotates around its short axis, showing alternately its side profile and its tip. The light curve of 3i Atlas, with its double-peaked pattern, indicates the latter the object presents its long profile twice per rotation, and its short profile twice per rotation, consistent with tumbling around the axis of maximum moment of inertia, the short axis perpendicular to the elongated direction. Only took 16 hours to complete one full rotation. For comparison, Earth rotates in 24 hours, Mars in 25, most asteroids in periods ranging from 5 to 20 hours, though some spin much faster and others much slower. The 16-hour period of 3i Atlas places it comfortably in the middle range, neither unusually fast nor unusually slow. This rotation was likely established long ago, perhaps during the collision or ejection event that sent the object into interstellar space, or perhaps through subsequent collisions during its first few million years in its home system, before it departed into the emptiness between stars. The axis of rotation itself remains fixed in space, pointing towards some arbitrary direction in the celestial sphere, unchanging as the object travels. This stability indicates the object is a rigid body, or at least rigid enough that internal friction has damped out any wobbling or precession. A loose rubble pile, an aggregate of smaller fragments held together only by weak mutual gravity, would likely exhibit more complex rotational behavior, energy dissipating through friction between components, the spin axis wandering over time. That 3i atlas maintains a stable rotation suggests it is either a monolithic piece, a single coherent rock or ice ball, or a well-settled rubble pile where components have shifted into stable configurations, locked into place by friction and interlocking geometries. The brightness variations themselves contain additional information beyond simple elongation. The maximum brightness occurs when the long axis of the object aligns perpendicular to the line of sight toward Earth, presenting the largest cross-sectional area. The minimum brightness occurs when the object is viewed end-on, along its long axis, presenting the smallest cross-section. But the transition between maximum and minimum is not symmetric in time. The brightness falls off more steeply after maximum than it rises before maximum, an asymmetry that could indicate one end of the object is larger than the other, or that the surface albedo varies, brighter on one hemisphere, darker on the other. Surface heterogeneity would not be surprising. Cosmic rays bombard interstellar objects continuously, and the radiation dose depends on exposure time and shielding. Surfaces facing the direction of travel through the galaxy receive higher fluxes of high-energy particles, gradually darkening as radiation breaks down surface materials and creates new compounds. Surfaces facing away receive less radiation, remaining comparatively pristine. Over millions of years, this differential weathering could create significant albedo contrasts, bright leading hemispheres and dark trailing hemispheres, or vice versa depending on the chemistry involved. Only took 1 million years of cosmic ray exposure to darken the surface measurably, perhaps less, depending on the initial composition and the radiation environment along 3i Atlas's path. The object may have traversed relatively empty regions of the interstellar medium, experiencing only the average galactic cosmic ray flux, or it may have passed near a supernova remnant or pulsar wind nebula, regions where particle fluxes spike dramatically higher. No way to know without a detailed map of the object's trajectory and timing, information that remains forever inaccessible given the uncertainties in the origin calculations. Thermal effects also influence rotation, though subtly. As the object tumbles, different surfaces heat and cool cyclically. The sun-facing side warms slightly, ice sublimating if temperatures rise high enough, dark surfaces absorbing radiation and conducting heat inward. The shadow side radiates heat into space, cooling back toward the ambient temperature of the solar system's outer reaches, a few tens of Kelvin above absolute zero. This thermal cycling could, in principle, create torques, the Yarkovsky effect, where absorbed sunlight and re-radiated thermal energy impart a tiny net force depending on the rotation rate and thermal properties. But at the distance 3i Atlas passes from the Sun, more than 600 million kilometers, sunlight is weak, heating minimal, and such effects likely negligible compared to the object's substantial angular momentum. The stable tumbling will continue for millions of years more. Likely, barring a collision with another interstellar object, an event so improbable as to be effectively impossible. Given the vast emptiness of space, nothing will alter the rotation significantly. The object will tumble through the outer solar system, tumble past the heliopause, tumble through the local interstellar medium, tumble through whatever molecular clouds or stellar encounters await in the galaxy ahead. The rotation is a relic, a frozen record of ancient dynamics, preserved by the vacuum and cold of interstellar space where friction does not exist and where time passes without meaningful change. What the rotation does not reveal is internal structure. A solid rock tumbles identically to a hollow shell of the same mass distribution and identically to a rubble pile of the same overall shape. Without measuring how the object responds to external forces, without observing tidal deformations or analyzing oscillation modes, the internal composition remains hidden. 3I Atlas could be solid nickel iron, or porous ice, or a mix of rock and ice, or a fractured remnant held together by tensile strength rather than gravity. The tumbling continues regardless, indifferent to what lies beneath the surface, displaying only the geometry and reflectivity of the exterior, the only aspects visible from millions of kilometers away. Comets are not known for their geometric perfection. In our solar system, cometary nuclei observed up close reveal irregular, fractured shapes, lumpy potatoes, contact binaries, fractured fragments. Comet 67P Churyumov-Gerasimenko, visited by the Rosetta spacecraft, resembles a rubber duck, two distinct lobes connected by a narrow neck. Comet Halley appears elongated and potato-shaped, scarred by impact craters and active vents. Comet Wild 2 shows a battered surface, deeply pitted, covered in steep-walled depressions where subsurface ice has sublimated away. These shapes arise from the nature of comets themselves, loose aggregations of ice and dust, primordial remnants from the solar system's formation. Objects that have spent billions of years in cold storage beyond Neptune's orbit, occasionally perturbed inward where solar heating vaporizes volatiles and erodes surfaces unevenly. The process begins with formation. Comets likely accumulate in the outer regions of protoplanetary disks, where temperatures remain cold enough for water ice and other volatiles to condense. Small grains of ice and dust stick together through electrostatic forces and gentle collisions, gradually building larger aggregates. The process is delicate. Velocities must remain low too fast and collisions shatter rather than merge. Gravity plays little role at these scales. The resulting bodies are porous, fluffy, density often less than half that of solid ice, more like cosmic snowballs than solid rock. They form as irregular clumps because there is no mechanism to smooth them, no heat to melt and refreeze them into spheres, no compression to compact them into uniform density. Over time, some comets remain in stable orbits in the Kuiper belt or Oort cloud, undisturbed for billions of years. Others get ejected, either inward toward the sun or outward into interstellar space. The mechanisms are gravitational interactions with planets. Especially giant planets like Jupiter can deflect comets dramatically, accelerating them to escape velocity with a single close encounter. During such encounters, tidal forces can deform the comet's shape. If the comet passes close enough to a massive body, the gravitational gradient across the comet's diameter becomes significant, stronger on the near side than the far side, stretching the object along the axis pointing toward the planet. Only took one close pass by Jupiter to reshape a comet entirely. The tidal forces during such encounters can exceed the comet's structural strength, particularly if the object is a loose rubble pile. The comet stretches, elongates, sometimes breaks apart entirely into multiple fragments that subsequently drift apart or remain loosely associated. Comet Shoemaker-Levy 9 famously broke into more than 20 distinct pieces during a close pass by Jupiter in 1992, then collided spectacularly with the planet 2 years later. Other comets survive tidal encounters but emerge elongated, their shapes permanently altered by the stretching forces. Even without tidal disruption, cometary shapes evolve through sublimation. As a comet approaches the sun, surface ices heat and vaporize, creating jets of gas that carry dust away from the nucleus. This outgassing is not uniform. Some areas sublimate more actively than others, depending on composition, surface temperature, solar illumination angle, and the presence of insulating dust layers. Active regions erode faster, creating pits, and depressions. Inactive regions accumulate dust, building up protective mantles that shield underlying ice. Over many orbits, these differential erosion processes sculpt the nucleus into increasingly irregular forms. The neck region of contact binaries is particularly vulnerable. If two lobes are connected by a narrow bridge, outgassing from that region can erode the connection over time, weakening it, perhaps eventually severing it entirely and producing two separate objects. Alternatively, the neck may simply thin further, creating ever more elongated dumbbell shapes. The exact outcome depends on the rate of erosion, the structural strength of the material, and whether the neck region contains more volatile or more refractory materials. For interstellar comets like 3I Atlas, these processes must have operated in a different stellar system under conditions that may differ from our own. Perhaps the parent star was more luminous, heating comets to higher temperatures during any perihelion passages. Perhaps the planetary architecture included more massive giants positioned differently, creating different gravitational dynamics. Perhaps the disk from which comets formed had a different composition, more carbon-rich, or silicon-rich, or volatile-rich, producing comets with different material properties and different responses to heating and tidal forces. Only took one system to produce 3I Atlas. Somewhere in the galaxy, conditions existed that formed this particular object, shaped it through whatever collisions or tidal encounters or sublimation episodes occurred, then ejected it into the void. The elongated form could represent any of several histories. It could be a tidal fragment, stretched during a close planetary encounter and then ejected before relaxing back to a more spherical shape. It could be a collision fragment, a shard broken from a larger parent body. It could be a contact binary, two smaller objects that merge gently and now tumble together through space. Or it could be a primordial form, an object that accreted, elongated, and has never been substantially altered. The lack of visible outgassing complicates interpretation. Typical comets become active when sunlight heats their surfaces above the sublimation temperature of their constituent ices around 150 Kelvin for water ice, lower for more volatile species like carbon monoxide or methane. 3. The Atlas, passing through the outer solar system at distances exceeding 600 million kilometers from the Sun, receives only weak sunlight, and surface temperatures likely remain below 100 Kelvin, too cold for significant water ice sublimation. If the object contains volatiles, they remain frozen, locked into the surface, invisible to remote observation. But the spectral hints of surface ice raise questions. Ice exposed to cosmic rays and ultraviolet light gradually transforms, becoming amorphous, developing a reddish or darkened crust through radiolysis. Fresh ice appears bright and reflective, bluish or neutral in colour. The spectrum of 3I Atlas suggests something intermediate ice that may be present but weathered, or mixed with dust, or partially covered by a dark lag deposit. This is consistent with an object that has resided in interstellar space for millions of years. Surface ice is slowly processed by radiation but never completely destroyed or buried. What remains unknown is the interior. Cometary nuclei often have onion-like structures, layers of different composition deposited at different times during formation, or mixed heterogeneously, depending on local conditions in the protoplanetary disk. Some regions are ice-rich, others dust-rich, creating variations in strength and erosion resistance. These internal structures determine how the object responds to stress, whether it fractures along pre-existing planes of weakness, whether it deforms plastically or shatters brittly, whether it can maintain an elongated shape or gradually relaxes toward a sphere under its own weak self-gravity. Only took billions of years to create comets in the first place. The time frames for their formation, evolution, and eventual ejection span the lifetime of planetary systems. 3C Atlas may have formed when its home star was young, still surrounded by a dense protoplanetary disk, or it may have formed later during a period of late heavy bombardment, or at any point in between. Its shape is a testament to processes that operated then and there, under conditions that can only be inferred, never directly observed. The object passes through now, silent and cold and elongated, carrying information encoded in its geometry, information that remains mostly inaccessible from this distance, at this resolution, with these instruments. The question of outgassing haunts every cometary observation. When a comet approaches the Sun, when surface temperatures rise above the sublimation point of volatile ices, the solid transforms directly to gas without passing through a liquid phase. Water ice sublimates, carbon monoxide sublimates, carbon dioxide sublimates, each at its own characteristic temperature, each producing vapor that expands into the surrounding vacuum, carrying dust grains along in the flow. This process creates the coma, the fuzzy atmosphere surrounding the nucleus, and eventually the tail, that iconic streamer of gas and dust pushed away from the Sun by solar wind and radiation pressure. Observers watch 3i Atlas carefully for any sign of such activity. They examine images for any hint of a coma, any fuzziness around the point source brightness of the nucleus. They search spectra for emission lines characteristic of gas, the hydroxyl radical at 308 nanometers, the carbon monoxide bands in the ultraviolet, the sodium D lines that sometimes appear when sodium atoms released from dust grains fluoresce in sunlight. They look for asymmetries in the light curve that might indicate jets preferentially erupting from one hemisphere. They calculate expected sublimation rates based on the object's distance from the Sun and estimated surface temperature, predicting how much gas should be produced if typical cometary ices are present. The observations show nothing. No coma appears in deep images stacked from multiple exposures. No emission lines emerge from the spectrum, at least none above the noise level. The object remains point-like, its brightness varying only with rotation, not with outgassing-induced changes. This absence of activity places 3i Atlas in a curious category. Either it contains no volatiles, having lost them long ago through previous passages near other stars, or through prolonged cosmic ray bombardment in interstellar space, or it contains volatiles that remain frozen at the temperatures it currently experiences, waiting for closer solar approach before sublimating. Only took 600 million kilometers of distance to keep the ices frozen. At this range from the Sun, solar flux is weak, about 3% of what Earth receives, barely enough to raise surface temperatures significantly above the ambient cold of space. Even a surface with low albedo, darkened by radiation processing, would struggle to reach 120 Kelvin under such weak illumination. Water ice remains stable. Carbon dioxide ice remains stable. Only the most volatile species, carbon monoxide, nitrogen, methane might sublimate at such temperatures, and only if they are present on the surface or close enough beneath to allow vapor to escape through pores in the overlying material. The absence of detectable outgassing does not mean the object is entirely inert. Small-scale sublimation could be occurring beneath the detection threshold of current instruments. A production rate of a few kilograms per second, perhaps a few tens of kilograms per second, would be undetectable in the observations, creating a coma too tenuous and faint to register against the background sky brightness and the glare from the nucleus itself. Yet such small rates would still be physically significant, representing the slow erosion of surface layers over days and weeks, the gradual release of volatiles accumulated during the object's journey through space. Alternatively, the surface may be mantled with a layer of non-volatile dust, a lag deposit left behind after ices sublimated during some previous warm episode, perhaps during the object's time in its home stellar system before ejection. Such mantles are common on comets in our solar system. As surface ice sublimates, dust grains once mixed into the ice remain behind, accumulating on the surface, eventually forming a cohesive layer thick enough to insulate underlying ice from solar heating. This crust acts as thermal armor, preventing further sublimation even if the object later approaches the Sun again. The crust can be quite thin, millimeters to centimeters, but effective, raising the surface temperature required for outgassing by tens of degrees. Only took one previous perihelion passage to create such a mantle, or perhaps the mantle formed through a different process, dust grains slowly accreting onto the surface during the object's passage through interstellar dust clouds, building up over millions of years, grain by grain, until a thin coating covered the original icy surface. Interstellar dust is sparse, only 1 grain per cubic kilometre in typical regions, but over millions of years and millions of kilometres of travel, the accumulated mass could become significant, microns or even millimetres thick. The spectrum offers hints, but not certainty. The weak absorption features that might indicate ice could also arise from other sources, silicate minerals with hydroxyl groups in their crystal structure, for instance, or organic compounds containing water of hydration. Disentangling these possibilities requires higher resolution spectroscopy than is currently available for such a faint, distant object. The signal-to-noise ratio limits what can be concluded. Astronomers speak carefully, using phrases like consistent with and possibly indicating rather than definitive identifications. What would happen if 3I Atlas passed closer to the Sun? This thought experiment interests researchers if the object's trajectory had brought it within, say, 300 million kilometers of the Sun. Closer than Mars, surface temperatures would have risen above 150 Kelvin. Water ice would begin sublimating, a coma might appear, jets might erupt from active regions. The object might brighten dramatically as dust-scattering sunlight filled the region around the nucleus, or perhaps nothing would happen, the surface mantle proving thick enough to insulate the interior, the object remaining stubbornly inactive despite the increased heating. This variability in cometary behaviour is well documented in our solar system. Some comets become highly active at large distances, sublimating volatile ices like carbon monoxide while still beyond Jupiter's orbit. Others remain dormant until passing within Earth's orbit, finally warming enough for water ice to dominate the outgassing. A few never become obviously active at all, appearing asteroid-like despite presumed icy composition, their surfaces too well armoured or their volatile content too depleted for significant sublimation to occur. Only took one trajectory to determine 3I Atlas would remain cold. The object's path through the solar system is fixed by celestial mechanics. The trajectory set when it entered the Sun's gravitational influence. Unalterable, except through rocket engines or gravitational assists from planets, neither of which apply here. The object will pass through the outer system and depart, never experiencing the temperatures that might reveal whether it harbours cometary ices or has long since lost them. Future observations may catch it as it exits, the geometry changing slightly, perhaps revealing new aspects of its shape or rotation. But the distance will only increase, the brightness only fade, the opportunity for detailed study already passing. The question of volatiles remains open. Does 3I Atlas contain pristine ices from its formation billions of years ago, preserved by the deep cold of interstellar space, waiting for some future stellar encounter to vaporize them? Or has it been processed by cosmic rays and ultraviolet light over millions of years? The ice is broken down into non-volatile residues, the object now essentially an asteroid despite its possible cometary origin. The observations cannot distinguish between these scenarios. The object keeps its chemical secrets, revealing only its shape and motion, the bare minimum required to confirm its interstellar origin and track its passage through our neighbourhood of space. Light carries information. When photons from the Sun strike the surface of 3I Atlas, some are absorbed and some are reflected, and the fraction reflected, the albedo, depends on the material composition and surface texture. Dark basaltic rock absorbs most visible light, reflecting perhaps 5%. Bright water ice reflects 70% or more when fresh, less after radiation darkening. Organic compounds, tholins produced by radiation processing of simple carbon and nitrogen molecules, absorb strongly at blue wavelengths while reflecting red, creating the characteristic ruddy appearance of many outer solar system objects. Spectroscopy dissects this reflected light, splitting it into component wavelengths, searching for the signatures of specific molecules and minerals. Each substance absorbs light at characteristic wavelengths corresponding to electronic and vibrational transitions in its molecular structure. Water ice shows strong absorption bands near 1.5 and 2.0 microns in the near-infrared. Carbon dioxide ice absorbs at 1.43, 2.0 and 2.7 microns. Organic materials create broad absorption across ultraviolet and blue wavelengths. Silicate minerals show features near 10 microns in the thermal infrared. By measuring the spectrum and identifying these absorption features, astronomers can constrain what the surface is made of, at least the outer few microns where photons interact before being absorbed or reflected. The spectrum of 3I Atlas remains frustratingly ambiguous. The object is faint, the reflected light weak, and obtaining a spectrum requires spreading that already weak light across many wavelength bins, reducing the signal in any single bin to near the noise level. Multiple observations are combined, stacking spectra to improve signal-to-noise ratio. But even then, the features remain subtle, tentative, requiring careful statistical analysis to determine whether they are real or artifacts of the noise. Only took a dozen hours of telescope time to gather the available spectral data. Not enough for definitive conclusions, but sufficient to rule out some possibilities and narrow the range of others. The spectrum appears relatively flat in visible wavelengths, neither strongly red nor strongly blue, suggesting a surface that is not dominated by pure ice nor by heavily processed organics. A slight upturn in reflectance toward red wavelengths hints at some radiation processing or the presence of organic compounds, but the effect is subtle, not the dramatic reddening seen on some Kuiper Belt objects or on Oumuamua. In the near-infrared, where water ice would show prominent absorption bands, the spectrum shows possible weak features, depressions in the reflected light at wavelengths consistent with ice. But the uncertainties are large. The features could be real, indicating water ice mixed with dust or partially covered by a dark mantle, or they could be noise, random fluctuations in the data that happen to fall near the wavelengths where ice absorbs. Astronomers assess the statistical significance, calculating the probability that such features would appear by chance, and the answer is equivocal, possible but not certain, suggestive but not definitive. The albedo itself provides constraints. By comparing the brightness of 3I Atlas with its estimated size, researchers calculate that the surface reflects approximately 15 to 25% of incident sunlight. Though the uncertainty range is wide, this falls between the extremes of very dark carbonaceous asteroids, which reflect less than 5%, and bright icy objects, which reflect 50% or more. The intermediate albedo suggests either a mixture of dark and bright materials, or a moderately reflective material uniformly distributed, or bright material partially covered by dark dust. Compositional mixing is common in the solar system. Few objects are compositionally pure. Most asteroids contain both silicate minerals and carbonaceous materials, the proportions varying depending on where they formed and what processing they experienced. Comets are mixtures by definition, ice and dust intimately combined, sometimes layered, sometimes homogeneously mixed. The ratio of ice to dust varies widely among comets, from ice-rich objects that produce spectacular comae to dust-rich objects that barely activate despite containing substantial volatiles. Only took one formation environment to determine the composition. The disk from which 3I Atlas formed, orbiting some distant star, had a temperature profile, a density profile, a compositional gradient reflecting the condensation sequence of different materials as distance from the star increased. Close to the star, only refractory materials like silicates and metals could condense too hot for ices. Farther out, water ice could condense, then carbon dioxide, then carbon monoxide and nitrogen and methane, each species condensing where temperatures dropped below its freezing point. The composition of objects forming at different distances reflects this gradient. Rocky in the inner regions, icy in the outer regions, with a transition zone where both rock and ice coexist. Where did 3I Atlas form? The spectrum does not answer this directly, but it provides clues. The possible presence of water ice suggests formation beyond the snowline, the distance from the parent star where water ice becomes stable. For a Sun-like star, this lies around 3 to 5 astronomical units, roughly the distance of the asteroid belt to Jupiter in our solar system. For a more luminous star, the snow line lies farther out, for a dimmer star, closer in. But regardless of the star type, objects containing water ice almost certainly formed in the cooler outer regions of their planetary systems. The lack of strong spectral features also carries information. Some Kuiper Belt objects show strong methane absorption bands, indicating methane ice on their surfaces. Others show ammonia hydrates, nitrogen ice, or complex organic compounds. 3 Atlas shows none of these clearly, suggesting either they are absent or present in concentrations too low to detect, or buried beneath surface layers of other materials. The simplest interpretation is that the object's surface composition is dominated by silicates and possibly water ice, with other materials either absent or volumetrically minor. Only took millions of years of cosmic ray exposure to alter surface chemistry. High-energy particles striking the surface break chemical bonds, rearrange atoms, create new molecules that would not form under equilibrium conditions. Simple ices like water and carbon dioxide can be converted into more complex organics through this radiolysis. Methane can polymerize into longer hydrocarbon chains. Nitrogen can combine with carbon to form nitriles and other nitrogen-bearing organics. The products are typically dark, reddish, refractory materials called tholins, residues that resist further processing and gradually accumulate on surfaces exposed to radiation over geological timescales. The spectrum hints at such processing but does not confirm it. The slight red slope, the intermediate albedo, the possible weak ice features all fit a picture of a surface partially covered by radiation-processed material. The original ices and minerals still present underneath but muted by an overlying layer of darker, chemically altered residue. This interpretation is plausible, consistent with the object's presumed age and exposure history, but alternative interpretations remain viable. The data are insufficient to distinguish between similar scenarios, between nearly identical compositional models that produce nearly identical spectra. What lies beneath the surface spectroscopy cannot answer. Light penetrates only microns into most materials before being absorbed or scattered back. The spectrum reveals the composition of the outermost surface layer, the skin of the object, but says nothing definitive about the interior. 3I Atlas could be homogeneous throughout, the same material from surface to core, or it could be layered or heterogeneous, with pockets and inclusions of different compositions. Without seismic measurements or gravitational field mapping or direct sampling, the interior remains hidden, inferred only indirectly from bulk properties like density and rotation. Only took as light to carry this much information, and light leaves much unanswered. The photons reflected from 3I Atlas encode the object's surface properties in their wavelengths and intensities, but extracting that information requires precise measurements and careful interpretation. And even then the conclusions are probabilistic, hedged with uncertainties, subject to revision as new data arrive or new models are developed. The object drifts outward, growing dimmer, the signal weakening, the window for spectroscopic study closing as observational noise begins to dominate the subtle features that might reveal what this traveller is made of. The hypothesis surfaces inevitably, as it has for every interstellar object detected so far. When something unusual passes through the solar system, when its shape or behaviour or trajectory defies easy explanation, someone suggests what if it is not natural, what if it is artificial, constructed rather than formed, a probe or spacecraft sent by another civilization. The speculation appears in popular media, in academic papers that carefully hedge their language, in press conferences where scientists acknowledge the possibility while emphasizing the improbability. For 3I Atlas, the extreme elongation triggers the question once more. Natural processes rarely create such shapes, the argument goes, but engineering could. A cylinder, a needle, a probe designed for efficient travel through interstellar space. Such geometries might be optimal for minimizing collisions with interstellar dust, or for maximizing surface area for radiators or solar sails. The hypothesis is not absurd on its face. The galaxy is old, 13 billion years at least, and Earth itself is only 4.5 billion. Civilizations could have arisen billions of years before humanity, spreading through the galaxy, sending probes to neighboring star systems, constructing artifacts that might still function millions of years after their creators vanished. The numbers support this logic. Estimates suggest hundreds of billions of stars in the Milky Way, many with planetary systems, some fraction of those planets potentially habitable. Even if technological civilizations are rare, even if they arise only once per million star systems, thousands should exist. Some might have developed interstellar travel, some might have sent exploratory probes to every nearby star, including ours, but extraordinary claims require extraordinary evidence, and 3D Atlas provides nothing extraordinary beyond its shape. It does not emit signals in radio wavelengths. It does not alter its trajectory in ways inconsistent with gravity. It does not exhibit propulsion or maneuvering. It tumbles passively, reflecting sunlight as any inert body would, obeying Kepler's laws with no deviations, showing no signs of active control or internal power sources. The shape alone, while unusual, is not unprecedented. Natural objects can be elongated. Collisional fragments are often irregular. Tidal disruption can stretch bodies into needles. The fact that such shapes are rare does not make them impossible, only infrequent. Only took one civilization to send Oumuamua before the hypothesis became commonplace. That object's elongation, combined with its unexplained non-gravitational acceleration, sparked serious academic consideration of artificial origins. One prominent astronomer published papers suggesting Oumuamua could be a light sail, a thin reflective surface pushed by starlight, its acceleration explained by radiation pressure. The hypothesis generated controversy and criticism, with most astronomers favouring natural explanations like outgassing or cometary fragmentation, but the debate itself was conducted seriously. Calculations performed, predictions made, evidence weighed. The scientific community treated the possibility with respect even while finding it unlikely. For 3I Atlas, the case is weaker. No unexplained acceleration has been detected. No anomalous properties beyond shape suggest artificiality. Occam's razor, the principle that simpler explanations are preferable when they fit the data equally well, favours natural origins. A tumbling rock or ice fragment, shaped by collisions or tidal forces or accretion processes, requires no new physics, no appeal to intelligence, no assumptions about alien technologies. An artificial probe requires all of these, plus additional assumptions about the probe's purpose, its age, its state of repair or decay, why it tumbles rather than maintaining orientation, why it reflects light passively rather than controlling its surface properties. The burden of proof falls on the extraordinary claim. To establish artificiality would require evidence of design symmetries inconsistent with natural processes, materials or isotope ratios not found in nature, signals or emissions indicating internal machinery, trajectory adjustments demonstrating propulsion. None of these have been detected. The observations show a tumbling elongated object following a hyperbolic orbit, behaviour entirely consistent with a natural interstellar fragment passing through the solar system by chance. Yet the hypothesis persists partly because it is unfalsifiable with current data. No observation of 3I Atlas can definitively prove it is not artificial, short of a close-up spacecraft mission that inspects the surface and finds no machinery. No artificial structures, only rock and ice and dust. Such a mission is not planned and likely will not be planned, given the difficulty of reaching interstellar objects during their brief transit through the solar system. The object will pass unvisited, its nature determined only by remote observation, and remote observation can rule out some artificial scenarios but not all. Only took 3 interstellar objects to establish a pattern of speculation. Each detection spawns renewed discussion of extraterrestrial probes. each unusual feature prompting questions about artificial origins. This reflects both the excitement of discovering such objects they are genuinely novel, genuinely from beyond our solar system, and the persistent hope that somewhere among the countless fragments drifting between stars, one might carry evidence of other minds, other technologies, other civilizations. That hope is not unreasonable. The universe is large and old, but hope is not evidence, and the absence of natural explanation is not evidence of artificiality. The scientific consensus remains that Three-Eye Atlas is almost certainly natural. The shape is unusual but not impossible. The lack of outgassing could indicate volatile depletion or a surface mantle, both common in comets. The spectral properties suggest rock and ice, materials abundant in planetary systems. The rotation is consistent with a rigid body tumbling after collisional or tidal disturbance. Every observation fits natural processes, and no observation requires invoking intelligence or technology. The hypothesis of artificiality remains in the realm of possibility, but falls far short of probability. Interesting to consider as a thought experiment but unsupported by the data. What would constitute convincing evidence? A signal would be compelling radio transmissions, laser pulses, any electromagnetic emission at frequencies and patterns inconsistent with natural sources. A trajectory change would be significant course corrections, acceleration perpendicular to the sun's gravity, maneuvers indicating propulsion. Spectral anomalies would be intriguing absorption, or emission lines from elements or molecules not found in natural astronomical environments, or present in ratios inconsistent with nucleosynthesis. Surface features inconsistent with natural weathering would warrant serious consideration. Straight edges, regular patterns, geometric shapes preserved despite millions of years of micrometeorite bombardment. None of these have been observed. Only took remote observation to establish what Three-Eye Atlas is not. It is not actively transmitting. It is not maneuvering. It is not made of exotic materials. It is not geometrically regular beyond what natural tumbling bodies exhibit. It is, by all available evidence, a rock or ice fragment from another star's planetary system, shaped by natural forces, ejected by gravitational interactions, travelling through space for millions of years, now passing through our solar system by chance before continuing into the galaxy beyond. The hypothesis of artificiality adds nothing to this explanation, predicts nothing new, explains nothing better. It remains a possibility in the technical sense that it cannot be absolutely disproven, but it is not a hypothesis that scientists working with the data find compelling or necessary. The conversation continues nonetheless, a reminder that extraordinary objects prompt extraordinary questions, even when the answers remain stubbornly ordinary. The violence of collisions shapes the small bodies of planetary systems, unlike planets, which grow large enough for self-gravity to pull them into spheres. Smaller objects, asteroids, comets, moonlets lack the mass to overcome the structural strength of their materials. They remain angular, irregular, their forms determined by the last major impact that fractured them or the accumulation process that assembled them. In asteroid belts and debris disks, collisions occur routinely over billions of years, a slow grinding process where larger bodies occasionally collide and shatter into smaller fragments. Those fragments collide and shatter further, creating a cascade of progressively smaller debris down to dust-sized particles that eventually spiral into the star or get blown away by radiation pressure. The physics of impacts governs what shapes emerge. When two asteroids collide at typical velocities several kilometers per second, the kinetic energy exceeds the gravitational binding energy of both bodies by orders of magnitude. The result is catastrophic disruption. Stress waves propagate through the rock or ice, exceeding the material's tensile strength, creating fractures that propagate and branch. The bodies shatter into fragments, each fragment's size and shape determined by the pre-existing internal structure, the presence of cracks or weak layers, the orientation of mineral grains. The largest fragments, those containing most of the original mass, become new asteroids in their own right, irregularly shaped, covered in fresh fracture surfaces, tumbling as they separate. These collisional fragments inherit angular, elongated geometries. A shard broken from a larger body has no reason to be spherical. It is shaped by fracture mechanics, by how cracks propagated through the parent body during impact. Some fragments are roughly a quant, their three axes similar in length. Others are elongated, one axis 2 or 3 or 4 times longer than the others, needle-like or blade-like depending on how the fractures intersected. The distribution of shapes follows from the statistics of random fracture. Most fragments are moderately elongated. A few are nearly spherical, a few are extremely elongated, with elongation ratios exceeding 4:1 or 5:1. Rare but not impossible. Only took one impact to create such a shard, or perhaps many impacts, each one chipping away at a larger body, gradually reducing it to smaller and smaller fragments. The final shape determined by the accumulated damage from millions of years of bombardment, in dense asteroid belts, where objects are numerous and collisions frequent. Most asteroids have been shattered and reassembled multiple times over the solar system's history. They are rubble piles, gravitationally bound aggregates of smaller fragments, held together by weak mutual gravity rather than material strength. These rubble piles can also be elongated if the component fragments arrange themselves asymmetrically, or if the pile formed from the collision of two separate bodies that did not quite merge completely. 3I Atlas could be a collisional fragment from its home system. Perhaps it originated in an asteroid belt orbiting another star, a belt dense with rocky and icy bodies left over from planetary formation. Perhaps a collision occurred there, two asteroids striking each other at high velocity, shattering into hundreds of fragments. Perhaps 3I Atlas was one of those fragments, elongated and irregular, carrying the scars of that ancient impact in its shape. Subsequently, gravitational perturbations from a giant planet in that system could have ejected it, sending it on a trajectory that eventually became unbound from the star, drifting away into interstellar space. The surface of such a fragment would bear witness to its violent past. Fresh impacts create rough textures, angular facets, sharp edges where fractures intersect. Over time, subsequent smaller impacts erode these features, smoothing edges, rounding corners, covering the surface with a regolith of pulverized rock and dust. But in the cold of interstellar space, where further collisions are vanishingly rare, these erosion processes halt. The surface remains largely as it was when the object left its home system, frozen in the state it achieved during its final millions of years of residence in the asteroid belt or Kuiper belt analogue where it formed. Only took a few million years of collisional evolution to shape the surface. Micrometeorites, tiny grains of dust, impact continuously at velocities of tens of kilometers per second, each impact vaporizing a small crater, ejecting material, gradually sandblasting the surface. In asteroid belts where dust is abundant, this process operates efficiently, grinding down surface features over timescales of millions to hundreds of millions of years. But once the object enters interstellar space, dust densities drop by many orders of magnitude. The bombardment rate becomes negligible. The surface effectively stops evolving, preserving whatever texture it possessed at ejection. Tidal forces add another mechanism for creating elongated shapes. If an object passes close enough to a planet or star, the gravitational gradient across its diameter can become significant. The side facing the massive body feels stronger gravity than the far side, creating a differential force that stretches the object along the direction toward the planet. For weak rubble, piles barely held together by self-gravity, even modest tidal forces can be disruptive, pulling the object apart or at least deforming it significantly. The Roche limit defines the critical distance inside this limit. Tidal forces exceed gravitational cohesion, and the object will disrupt. Outside this limit, the object survives but may be stretched or deformed. Objects that survive a close tidal encounter often emerge elongated. The stretching forces preferentially pull material toward the axis pointing at the planet, creating a cigar-shaped or football-shaped geometry. If the object is a rubble pile, the components may shift and rearrange, settling into a new equilibrium configuration that is more elongated than the original. If the object is solid, it may develop internal fractures, cracks that propagate along the stretched axis, weakening the structure and allowing subsequent impacts to fragment it more easily along that direction. Only took one tidal encounter to reshape an object permanently. Comet Shoemaker-Levy 9's encounter with Jupiter in 1992 stretched it into a chain of fragments, each fragment a distinct piece separated from its neighbours by the tidal forces. Not all objects break apart so dramatically. Some are stretched but remain intact. Their shapes altered but their cohesion preserved. Whether an object survives or disrupts depends on the strength of tidal forces, the structural strength of the object, and the velocity of the encounter. Faster encounters allow less time for tidal forces to act, reducing the total deformation. For 3I Atlas, the specific history remains unknowable from the available data. The object's shape is consistent with collisional fragmentation, with tidal stretching, or with some combination of both, or with primordial elongated accretion, in a low-density environment where objects did not collide often enough to break each other apart. Each scenario is physically plausible. Each has examples in the solar system, collisional fragments in the asteroid belt, tidally disrupted moons around giant planets, contact binaries in the Kuiper belt. The uncertainty is irreducible without more detailed observations or, ideally, a sample return mission that could analyze the object's internal structure and surface composition directly. What can be said is that violent events likely played a role. Elongation ratios of 4:1 or greater do not arise from gentle processes. Something stressed this object, either pulling it apart or breaking it from a larger parent body, imposing the shape it now carries. That shape has been preserved for millions of years by the stability of interstellar space, carried across light years as a frozen record of ancient dynamics, a relic of forces that operated in another solar system under another sun, in epochs when Earth was perhaps younger, perhaps not yet bearing life, perhaps still a barren world of rock and water awaiting the slow chemistry that would eventually produce biology. Density constrains composition. An object's mass divided by its volume yields average density, and different materials have characteristic densities that narrow the possibilities for what lies inside. Pure water ice has a density of about 920 kilograms per cubic meter. Silicate rock ranges from 2,500 to 3,500 kilograms per cubic meter, depending on mineralogy. Iron and nickel, the metals common in asteroids and planetary cores, have densities near 8,000 kilograms per cubic meter. By measuring or estimating an object's density, researchers can infer whether it is predominantly icy, rocky, metallic, or some mixture. For 3I Atlas, neither mass nor volume is known with certainty. The volume can be estimated from the object's brightness and assumed albedo, but this calculation depends on knowing the shape, which is itself uncertain beyond the general conclusion of elongation. The mass cannot be measured at all without observing gravitational effects on nearby objects or spacecraft, neither of which is available for a solitary interstellar visitor passing through empty space millions of kilometers from anything else. Density thus remains unconstrained by direct measurement, inferred only through comparison with similar objects and plausible formation scenarios. If the object is a comet, density likely falls below 1,000 kilograms per cubic meter, possibly much lower. Cometary nuclei observed up close by spacecraft missions have revealed surprisingly low densities, often around 500 kilograms per cubic meter, sometimes less. Comet 67P Churyumov-Gerasimenko, studied extensively by the Rosetta mission, has a density of 533 kilograms per cubic meter, barely more than half the density of water ice. This implies high porosity. The nucleus is not solid ice, but rather a mixture of ice and dust with substantial empty space, voids and cavities and pores permeating the structure. Such low-density objects are often described as rubble piles or fluffy aggregates, barely held together by their own weak gravity. more like cosmic dust bunnies than solid rocks. Only took a few spacecraft missions to overturn assumptions about cometary structure. Before close-up observations, many models assumed comets were relatively solid, perhaps porous but still coherent, with densities approaching that of pure ice. The actual measurements showed something far more tenuous, structures so porous that, if you could somehow stand on the surface, you might sink into the material under your own weight, the weak cohesion insufficient to support even modest pressures. These low densities also explain why comets are so fragile, why some break apart spontaneously during close solar approaches, thermal stresses and internal gas pressures exceeding the minimal strength holding the structure together. If 3I Atlas is an asteroid, density likely exceeds 2,000 kilograms per cubic meter, perhaps reaching 3,000 or higher. Rocky asteroids observed in the solar system show a wide range of densities reflecting different compositions and porosities. Carbonaceous asteroids, rich in carbon compounds and clays, have lower densities, around 500 to 2,000 kilograms per cubic meter. Silicate asteroids, composed mainly of rocky minerals, range from 2,500 to 3,500 kilograms per cubic meter. Metallic asteroids, remnants of differentiated bodies whose rocky mantles have been stripped away by collisions, can reach density above 7,000 kilograms per cubic meter. Iron-rich and heavy, porosity complicates the relationship between composition and density. Even solid rock can have lower than expected density if it contains voids, cracks, pores, fractures, or spaces between rubble pile components. Many asteroids are indeed rubble piles, gravitationally bound collections of fragments produced by collisions that shattered the original body but did not provide enough energy to disperse the fragments completely. These rubble piles have macroporosity, empty space between large fragments, reducing the overall density below what the constituent materials would suggest. Microporosity, small pores within individual fragments, further reduces density. Only took collisional disruption to create a rubble pile. When asteroids collide catastrophically, the fragments initially fly apart, but if the impact energy is insufficient to reach escape velocity, the fragments eventually fall back together under mutual gravitational attraction, reaccumulating into a new body. This body is a rubble pile by construction, loosely bound, highly porous, shaped by how the fragments happen to stack and settle. The process has happened countless times in the asteroid belt, creating a population where rubble piles may actually outnumber monolithic bodies, though distinguishing between them from remote observation is difficult without detailed gravitational measurements or observations of tidal disruption. The internal structure of 3I Atlas remains entirely speculative. It could be a monolith, a single coherent piece of rock or ice with some intrinsic strength beyond gravitational cohesion. It could be a rubble pile, a collection of smaller fragments held together by gravity, porous and weak. It could be intermediate, a fractured body with large cracks and faults but still somewhat coherent, individual fragments interlocked or frozen together by ice acting as cement. Each possibility has different implications for density, for strength, for how the object would respond to stresses like tidal forces or rotational acceleration. The rotation provides a weak constraint. The fact that 3I Atlas tumbles stably with a constant period suggests it is not actively falling apart, not so weak that rotational forces or thermal stresses are pulling it into pieces. Objects on the verge of disruption often show irregular rotation, their spin rates changing as material shifts internally or as pieces break off. The stability observed in 3I Atlas suggests at least modest cohesion, enough to maintain integrity over the timescales of observation, months at least, likely much longer given that the object has presumably been rotating similarly for millions of years without flying apart. Only took one measurement to establish rotation stability, though continued monitoring might reveal subtle changes. If the rotation period were lengthening or shortening detectably, that would indicate torques acting on the object outgassing producing jet forces, tidal interactions with the sun or planets, or internal stress relaxation. None of these effects have been observed. supporting the interpretation that 3i Atlas is essentially inert and dynamically stable, tumbling unchanged through the solar system as it has tumbled through interstellar space. The shape itself provides indirect evidence about internal structure. Highly elongated shapes are difficult to maintain for weak rubble piles, because self-gravity tends to pull material toward the centre of mass, rounding out protrusions and filling in cavities over time. An elongated rubble pile needs either to be rotating rapidly, centrifugal forces supporting the elongation against gravity, or to have sufficient internal friction and interlocking between components to resist gravitational collapse. The 16-hour rotation period of 3i Atlas is too slow for significant centrifugal support, suggesting either the object is monolithic or it is a rubble pile, with strong enough friction to maintain its shape. What lies at the centre is there a dense core, perhaps metallic, left over from differentiation if the object originated in the interior of a larger, once molten body? Or is the interior compositionally homogeneous, the same mix of rock and ice throughout, reflecting condensation and accretion in a protoplanetary disk where no melting occurred, without seismic measurements that could map internal density variations, without gravitational field measurements that could reveal mass distribution asymmetries? The interior remains hidden. The surface and the overall behaviour provide only the most general constraints, not so dense as pure metal, not so light as pure porous ice. Something in between, something consistent with mixed rock-ice composition or porous rock or volatile depleted comet material. Only took remote observation to learn this little density. That fundamental property linking composition to structure remains uncertain by factors of 2 or 3, the range of plausible values spanning from cometary to asteroidal regimes. The object carries its mass through space, warps space-time by an infinitesimal amount according to its gravitational field, but that field is too weak and too distant to measure from Earth. The mass stays hidden, encoded in the object's resistance to acceleration, in the gravitational self-energy that binds it together, in the internal pressure gradients that might exist deep inside all properties invisible to remote observers watching faint reflected light from millions of kilometers away. The limitations accumulate like dust. Every observation of 3i Atlas is constrained by distance, by the faintness of reflected light, by the brief window during which the object remains bright enough for detailed study, by the capabilities of current instruments, by atmospheric turbulence that blurs ground-based images, by the economics of telescope time allocation, where hundreds of projects compete for access to the best instruments. What astronomers can measure is a fraction of what they would like to measure, and what they can conclude with confidence is a fraction of what the measurements might suggest. The surface remains largely mysterious. Spectroscopy provides wavelength-averaged information about composition, but it cannot map the distribution of different materials across the surface. Are there bright patches and dark patches, ice-rich regions and dust-rich regions? Does one end of the elongated object differ in composition from the other? Are there impact craters visible at the resolution current instruments could achieve? The observations cannot answer. The object appears point-like in all images, its angular size far too small to resolve into a disk that could be mapped. Even the largest telescopes on Earth, even space telescopes, see 3 Atlas as a single pixel, a dot whose brightness varies with rotation but whose internal structure remains invisible. Only took several million kilometers of distance to erase surface detail. At its closest approach to Earth, 3i Atlas lies hundreds of millions of kilometers away. An angular resolution, the ability to distinguish separate features, scales inversely with distance. An object 600 meters long at a distance of 600 million kilometers subtends an angle of roughly 0.2 milliseconds. The Hubble Space Telescope, with its 2.4-meter mirror, achieves resolutions around 50 milliseconds in visible light under ideal conditions. The object is 250 times smaller than what Hubble can resolve. Ground-based telescopes with adaptive optics, compensating for atmospheric blurring, achieve similar or slightly better resolution, but still fall short by orders of magnitude. Resolving surface features would require angular resolutions approaching microarc seconds, achievable only with interferometry combining light from multiple telescopes, separated by hundreds of meters or kilometers, effectively creating a telescope with an aperture equal to the baseline between instruments. Such interferometric observations are technically challenging, requiring precise synchronization and atmospheric correction, and have rarely been attempted for faint-moving targets like asteroids and comets. For an interstellar object passing through briefly, the logistical difficulties multiply. By the time observing programs can be organized and scheduled, the object has already receded, its brightness fading below the threshold where interferometry becomes feasible. The spectrum itself is incomplete. Spectroscopy has been obtained primarily in visible and near-infrared wavelengths, where the object reflects solar radiation. But thermal emission in the mid-infrared, which depends on the object's temperature and emissivity, has not been measured with sufficient precision to constrain thermal properties. Ultraviolet observations, which could reveal different mineralogies or organic compounds, are limited by the object's faintness and the scarcity of ultraviolet-capable telescopes. Far infrared and submillimeter observations, which might detect coal dust in a tenuous coma if one exists, have not been attempted because the expected signal is vanishingly small. Only took economics to limit what can be observed. Telescope time is expensive, allocated through competitive proposals where researchers must justify why their project deserves access over others. An interstellar object is scientifically interesting, certainly, but how much telescope time should be devoted to characterizing one faint, distant object, when that same time could be used for surveys that discover hundreds of new asteroids or comets, for spectroscopic studies of planetary atmospheres, for observations of distant galaxies or exoplanets? The trade-offs are real, the resources finite, and 3i Atlas receives what attention it can command, but not unlimited attention. Not every observation that might ideally be performed. The rotation axis orientation remains uncertain within tens of degrees. Observers can determine the rotation period from the brightness variations, but the orientation of the spin axis in space requires more detailed modelling of how the light curve changes as the observing geometry shifts. As 3i Atlas moves through the solar system, the angle between the observer, the Sun, and the object changes, and these geometry changes should, in principle, cause systematic variations in the light curve shape and amplitude. By modelling these variations, researchers can infer the spin axis direction. But the observations are noisy, the variations subtle, and multiple axis orientations can produce similar light curve patterns, leaving ambiguities that cannot be resolved with current data. Only took a few degrees of uncertainty to propagate through calculations. The spin axis orientation affects estimates of the object's elongation, its surface properties, even its size. Models that assume one orientation may conclude the object is moderately elongated with moderate albedo. Models assuming a different orientation may conclude it is extremely elongated with low albedo. Both conclusions are consistent with the data within uncertainties, and distinguishing between them requires better signal-to-noise ratios or longer baseline observations than are available. The trajectory also carries uncertainties, though smaller. Astrometric measurements, precise determinations of the object's position against background stars, accumulate over weeks of observation, and from these positions the orbit can be calculated. The hyperbolic trajectory is well established, the eccentricity exceeding 1, the object clearly unbound from the solar system, but the exact values of orbital elements have uncertainties, and these uncertainties grow when extrapolating the trajectory backward in time to infer the object's origin or forward in time to predict its future path. Small measurement errors in position and velocity now translate into large uncertainties in where the object was millions of years ago or where it will be millions of years hence. Compositional ambiguities persist. The spectral features that might indicate water ice could also arise from hydroxylated minerals. Phyllosilicates containing water bound in their crystal structure. The red slope that might suggest organic processing could also result from iron oxidation states in silicate minerals. The intermediate albedo that might indicate a mixture of ice and dust could also represent uniformly grey rock. Each spectral characteristic admits multiple interpretations, and while some interpretations are more likely than others, based on what is known about solar system objects, none can be definitively excluded. Only took faint light to create such ambiguity. The signal-to-noise ratio in spectra determines how confidently features can be identified. Weak features near the noise level might be real absorption bands or might be statistical fluctuations. Increasing signal-to-noise requires longer integration times, larger telescopes, or brighter objects. As 3i Atlas recedes and dims, the signal-to-noise ratio decreases, and weak features disappear into noise, taking with them the information they might have carried about composition or surface properties. The internal structure remains entirely opaque, without gravitational measurements, without seismic signals from impacts or thermal cracking, without radar observations that could penetrate the surface. The interior is unknowable. Is it solid or porous, homogeneous or layered? Does it contain voids, or is it packed dense? These questions await a spacecraft mission that can approach closely, that can orbit the object and map its gravitational field, that can fire instruments at the surface or even land and drill. No such mission is planned, and planning one would be difficult given the object's high velocity and unfavourable trajectory, requiring either enormous fuel reserves or gravitational assists, carefully choreographed years in advance. What remains is the archive of observations, the collection of images and spectra and photometric measurements gathered during the weeks when 3i Atlas was bright enough to study. These data will be analysed and reanalyzed as techniques improve, as new models are developed, as understanding of interstellar objects advances with each new detection. But the fundamental limitations cannot be overcome retroactively. The resolution cannot be improved beyond what the instrument and distance allowed. The signal-to-noise cannot be enhanced beyond what the exposure time and detector sensitivity provided. The object itself is gone, moving away, fading into invisibility, taking its answers with it, leaving only the incomplete record of what could be measured when it passed through. The trajectory continues outward, the path determined by celestial mechanics with the inevitability of equations, having reached its closest approach to the Sun. 3i Atlas now climbs back out of the gravity well, slowing as it rises, trading kinetic energy for gravitational potential energy, the distance increasing daily, the solar flux weakening, surface temperatures dropping back toward the ambient cold of interstellar space. The object will never return. The hyperbolic orbit guarantees this eccentricity greater than 1 means the trajectory is open, unbound, a one-way passage through the solar system with no possibility of capture, no mechanism to circularize the orbit and make the object a permanent resident. The velocity relative to the Sun, currently around 32 kilometers per second, will decrease as the object moves farther from the solar system's center of mass. At large distances, far beyond the orbits of the planets, far beyond the Kuiper belt, the velocity asymptotically approaches what is called the hyperbolic excess velocity, the speed the object possessed at effective infinity before entering the Sun's gravitational influence, and the speed it will possess again when it returns to effective infinity after leaving. For 3i Atlas, this hyperbolic excess velocity is approximately 26 kilometers per second, somewhat slower than when it entered because the gravitational interaction has bent the trajectory, redirecting the object's motion slightly, altering its direction but conserving total energy. The heliopause lies ahead, roughly 120 astronomical units from the Sun, the boundary where the solar wind, the stream of charged particles flowing outward from the Sun, meets the interstellar medium and is no longer strong enough to push back the external pressure. Crossing this boundary takes time even at interstellar velocities. 3i Atlas, travelling at 26 kilometers per second, covers 1 astronomical unit in about 60 days, Reaching the heliopause from its current position will require several decades, years stretching into decades, the object drifting through the outer reaches of the solar system, where sunlight is so dim that high noon resembles deep twilight on Earth, where temperatures hover just above absolute zero, where the only planets are distant Uranus and Neptune, themselves faint dots barely distinguishable from stars to any observer on the object's surface. If there were observers, which there are not, only took a century or so to cross from the inner system to beyond the heliopause. The solar system is large in human terms, distances measured in billions of kilometers, but small compared to interstellar distances. The nearest star, Proxima Centauri, lies more than 4 light-years away, roughly 265,000 astronomical units, more than 2,000 times farther than the heliopause. At 26 kilometers per second, 3 Atlas would require roughly 80,000 years to reach Proxima Centauri if it were headed in that direction, which it is not. The object is headed elsewhere, towards some region of the galaxy determined by its trajectory through the solar system, which was itself determined by the trajectory it possessed upon entering, which was determined by its path through the galaxy over the preceding millions of years. The stars are not fixed. They orbit the galactic center on their own paths, moving relative to each other, drifting slowly through space as the galaxy rotates and evolves. The Sun orbits at roughly 220 kilometers per second, completing one orbit around the galactic center every 230 million years. Other stars move at similar speeds but in different directions, creating a complex flow pattern where nearby stars approach or recede depending on their individual orbital velocities. 3I Atlas moves through this flow, its velocity relative to the local standard of rest, the average motion of stars in the solar neighborhood, determining which stars it will eventually approach, though approach at interstellar scales means passing within a few light years, not colliding, not even coming particularly close by planetary system standards. Calculating the object's future trajectory requires knowing its velocity vector precisely, and uncertainties in that velocity propagate over time. A measurement error of just 1 meter per second translates into a positional uncertainty of tens of billions of kilometers after 1 million years of travel, hundreds of light years after 10 million years. At such uncertainties, predicting which specific star system 3I Atlas might pass near becomes impossible. What can be said is that the object is headed in a general direction, toward a particular region of the sky, and over the next few million years it will pass through that region, encountering whatever stars happen to lie along or near its path. Only took 3 measurements to define the trajectory well enough for near-term prediction. Over the next few centuries, the path of 3I Atlas can be calculated with reasonable precision, accurate to within a few million kilometers. Over the next few millennia, uncertainties grow but remain manageable, perhaps tens of millions of kilometers. Beyond that, galactic dynamics become important. The gravitational influence of the galaxy's disk, the spiral arms, the local density of stars and dark matter, all contribute subtle forces that accumulate over millions of years, perturbing trajectories in ways that depend on the detailed structure of the galaxy, which is itself uncertain. The object will eventually pass near other stars. Probably. Space is vast and empty, but stars are numerous. The galaxy contains hundreds of billions of them, and while the average separation is several light years, statistical arguments suggest that over millions of years, 3 Atlas will pass within a few light years of hundreds of stars, within 1 light year of dozens, perhaps within 1/10 of a light year of a few. Such close passages, while not close enough for gravitational capture, might alter the trajectory slightly, the star's gravity deflecting the object's path by small angles, changing its velocity by a few meters per second or a few tens of meters per second. If 3I Atlas passes through another star's planetary system, if it crosses through the region where planets orbit, then more interesting dynamics could occur. A close encounter with a giant planet could deflect the object dramatically, either accelerating it further into the galaxy or even, in rare cases, capturing it into orbit around that star. Capture is improbable. It requires fine-tuned timing and geometry, but not impossible. Some fraction of interstellar objects passing through planetary systems are captured, becoming long-period comets or distant asteroids. Former interstellar wanderers now bound to new stars. Others are simply deflected, their trajectories bent, their speeds altered, their futures redirected toward different regions of the galaxy. Only took one close encounter with a planet to send 3i Atlas into interstellar space originally. Another such encounter, millions of years hence, could alter its trajectory again. A random walk through the galaxy, guided by gravitational interactions that are deterministic individually, but stochastic in aggregate. The object's long-term fate determined by which stars it happens to pass near, which planets it happens to encounter, which molecular clouds it might traverse, none of which can be predicted from current observations, all of which lie in the domain of probability rather than certainty. The timescales are staggering. Earth will experience millions of sunrises and sunsets, while 3i Atlas coasts through the dark. Continents will drift. Mountains will rise and erode. Species will evolve and go extinct. Ice ages will come and go. Perhaps civilizations will rise and fall. Perhaps humanity will spread beyond Earth, or perhaps disappear. And through all of this, the object will continue, unchanged, except for the occasional micrometeorite impact, the slow accumulation of interstellar dust on its leading surface, the gradual weathering by cosmic rays. It will pass through regions where a star formation is occurring, nebulae glowing with the light of newly born stars, and through regions where stars have already exhausted their fuel and collapsed into white dwarfs or neutron stars or black holes. The stellar corpses that litter the galaxy, reminders of entropy and the second law, the inexorable decay of ordered energy into heat. The object carries no memory of its origin, no record accessible without laboratory analysis of its composition and isotope ratios. It carries no awareness of its journey, no experience of time or motion, or the slow transit through cosmic distances. It simply continues, obedient to physics, following the geodesics of space-time, a mote of rock and ice adrift in the galaxy. One among billions or trillions of similar objects, the debris of planetary formations scattered across light years, a slow dispersal that operates over timescales measured in the rotation periods of galaxies. It moves toward silence, toward invisibility, toward the eventual fate of all small objects unattached to stars' eternal cold, eternal darkness, eternal motion through a universe that expands and cools and spreads matter ever more thinly across an ever larger volume of space. What it teaches us accumulates slowly, each observation a small correction to understanding, each interstellar visitor refining models of how planetary systems form and evolve and shed their debris into the galaxy. Before 2017, before Oumuamua, the existence of interstellar objects was theoretical, predicted by simulations of planetary dynamics, but never confirmed observationally. The simulations showed that during the chaotic early phases of planetary system formation, when giant planets migrate inward or outward, when gravitational interactions scatter smaller bodies in all directions, significant fractions of the original material, perhaps 10%, perhaps more, get ejected entirely, flung into interstellar space at velocities exceeding the star's escape velocity. These ejection events are common, occurring in most if not all planetary systems as they evolve toward gravitational stability. Young systems are dynamically hot, full of objects on crossing orbits, collisions frequent, gravitational interactions violent. Over millions of years, order emerges from chaos. Planets settle into stable orbits, cleared of smaller debris through collisions or ejections. The leftovers asteroids, comets, distant icy bodies remain in relatively stable reservoirs, asteroid belts and Kuiper belt analogues. occasionally perturbed inward by gravitational resonances or stellar encounters, but mostly stable, mostly quiescent. The objects ejected during the initial chaos become the galaxy's interstellar population, drifting between stars, a vast reservoir of material that exceeds by far the mass remaining in any individual planetary system's asteroid or comet belts. Only took one detection to prove this population exists. Oumuamua's discovery in 2017 confirmed what theory predicted, that interstellar space is filled with debris from planetary systems, fragments drifting through the void, occasionally passing through other systems by chance. The detection rate depends on how many such objects exist and how good detection capabilities are. Improved sky surveys, automated telescopes scanning large areas repeatedly, increase the chances of catching these objects during their brief transits through the inner solar system where they are bright enough to detect. 3 Atlas adds to the statistical sample, increasing from 2 to 3 the number of confirmed interstellar objects, tripling the data set from which inferences can be drawn. 3 is still too few for robust statistical conclusions, but patterns begin to emerge. The objects show diverse properties, different shapes, different compositions, different sizes, suggesting that the interstellar population is heterogeneous, reflecting the diversity of conditions under which planetary systems form. Some stars are metal-rich, their protoplanetary disks containing higher concentrations of silicates and iron, producing rockier objects. Some stars are metal-poor, producing ice-rich objects. Some systems form massive giant planets that dominate the dynamics, ejecting mostly small icy bodies from the outer system. Other systems form different architectures, ejecting different types of debris. The shapes are particularly informative. The extreme elongation of Oumuamua and the significant elongation of 3I Atlas suggest that highly elongated objects may be common in the interstellar population, more common perhaps than in our own asteroid and comet populations, where elongation ratios exceeding 3 to 1 are rare. Why might interstellar objects be more elongated? One possibility is selection bias. Elongated objects produce larger brightness variations, making them easier to recognize as unusual and therefore more likely to be flagged as potential interstellar objects requiring follow-up observation. Another possibility is that the ejection process itself favors elongated shapes. Tidal forces during close planetary encounters, preferentially ejecting objects that have been stretched or fragmented, only took 2 highly elongated objects to raise the question. If future detections continue showing elongation as a common characteristic, it would suggest something fundamental about how objects are shaped during ejection, or about what kinds of objects are most easily ejected. Alternatively, if future detections show more spherical objects, it would suggest that Oumuamua and 3I Atlas are outliers, unusual examples not representative of the broader population. With only 3 objects, the answer remains open, the statistics insufficient to draw firm conclusions. The velocity distribution also carries information. Objects ejected from planetary systems inherit velocity distributions that depend on the ejection mechanism and the gravitational dynamics of their home systems. Objects ejected by giant planets during early migration might have higher velocities than objects ejected later by smaller perturbations. The velocities of Oumuamua, Borisov, and 3I Atlas cluster around 20 to 30 km per second relative to the local standard of rest, typical for objects ejected gravitationally rather than through more exotic mechanisms like supernova explosions or stellar flybys, which would produce higher velocities. This clustering suggests most interstellar objects originate from relatively gentle ejection processes, typical planetary dynamics operating over millions of years rather than catastrophic events. The objects are not fragments from exploded planets or debris from stellar collisions, but rather the normal byproducts of planetary system formation, cast off during the sorting process that creates stable architectures. This implies that every star with planets contributes to the interstellar population, that the galaxy is filled with a continuous influx of new interstellar objects as planetary systems everywhere undergo dynamical evolution and eject their excess material. Only took a few billion years for the galaxy to fill with such objects. Current estimates, extrapolating from the detection rate and accounting for observational biases, suggest there may be trillions or even quadrillions of interstellar objects larger than 100 meters in the galaxy, perhaps one for every cubic astronomical unit of space, invisible because they do not emit light, detectable only when they pass close enough to a star to reflect significant sunlight. Most will never be detected. Most will drift through the galaxy forever unseen, their existence inferred statistically but never confirmed observationally. The compositional diversity hints at the range of environments where planets form. Borisov's cometary activity showed that some planetary systems produce volatile-rich objects similar to our own comets, water ice and carbon monoxide abundant, suggesting formation beyond the snowline in regions cold enough for these ices to condense. 3IE Atlas's possible ice features but lack of activity suggest either a different thermal history or a different compositional mix, perhaps less volatile-rich, perhaps more heavily processed by radiation. Oumuamua's lack of detected volatiles despite passing very close to the Sun suggests either complete volatile depletion or a composition dominated by refractory materials, rock or metal rather than ice. These differences teach that planetary systems are not all alike, that the mix of materials available during formation varies from star to star, that the processes shaping small bodies' collisions, heating, radiation processing operate differently in different environments. Each interstellar visitor is a sample from another system's formation history, a probe carrying information about conditions light years away and millions of years in the past. Information encoded in composition and structure and dynamic state. Readable if the observations are detailed enough, if the sample size grows large enough to distinguish patterns from noise. Only took 3 objects to begin learning. As detection capabilities improve, as more all-sky surveys come online, as automated data analysis becomes more sophisticated at identifying fast-moving objects with hyperbolic orbits, the detection rate will increase. Perhaps 1 interstellar object per year, perhaps more, each one adding to the dataset, each one constraining models of planetary formation and evolution, each one a small piece of the larger puzzle of how stars and planets and small bodies interact over billions of years to create the galaxy we observe. 3i Atlas is a chapter in that story. One data point among the thousands or millions that will eventually be needed to fully understand the interstellar population, its origins, its diversity, its role in redistributing material across the galaxy over cosmological timescales. The silence after is not sudden but gradual, a fading rather than a cessation. Observations of 3i Atlas continue as long as the object remains bright enough to detect, as long as telescope time can be justified, as long as there is hope of extracting new information from the dimming signal. But brightness follows an inverse square law with distance, and as the object moves farther from both the Sun and Earth, the reflected light weakens rapidly. An object twice as far reflects 1/4 the light, 4 times as far, 1/16. The decline is inexorable, dictated by geometry and physics. No amount of technological improvement can overcome the fundamental relationship between distance and flux. Astronomers continue measuring positions, refining the orbit, ensuring the trajectory calculations are as accurate as possible before the object fades completely. They continue photometry when feasible, watching for any changes in brightness or rotation that might indicate outgassing, beginning as the object cools further, or structural changes, or any anomalous behavior worth noting for the archive. They attempt final spectroscopic observations with the largest telescopes available. Long integration times stacking photons to achieve signal-to-noise ratios barely sufficient for analysis. Knowing these will be the last spectra obtained, the last chance to detect compositional features before the object disappears from reach, only took a few months from discovery to final observation. By early 2025, 3i Atlas has faded below 20th magnitude, invisible to all but the largest professional telescopes, and even those can barely detect it, the object appearing as a faint smudge on long exposures, position measurable, but brightness uncertain, spectrum unattainable. Observing proposals submitted for the following semester do not include 3i Atlas. There is nothing more to be learned with available instruments. The object too faint, the data quality too poor, the resources better allocated elsewhere. The observations cease. The object continues without witnesses. The archive remains. Every image, every spectrum, every photometric measurement is stored in astronomical databases, accessible to researchers who may, years or decades hence, return to this data with new analysis techniques, new models, new questions. Data from interstellar objects are particularly valuable because they are so rare, each observation irreplaceable, the opportunity lost once the object departs. Future astronomers will mine these archives, comparing 3i Atlas to later discoveries, searching for patterns, testing hypotheses about interstellar populations that can only be evaluated with statistical samples too large to collect in any single observing campaign. The object itself is beyond caring about observations or archives or scientific conclusions. It continues outward through the outer solar system, past the orbit of Neptune, toward the scattered disk and the Oort cloud, regions where the sun's gravity still dominates but weakly, where objects orbit at distances measured in thousands of astronomical units, where orbital periods extend to millions of years. 3 Atlas will not linger in these regions. Its trajectory is too energetic, too inclined, too fast. It will pass through in decades rather than millennia, a brief transit through the sun's most distant domain before crossing the heliopause into true interstellar space. Only took one passage through one solar system to add this object to humanity's catalogue of known interstellar visitors. Somewhere in the galaxy, other objects are entering other stellar systems, passing through their asteroid belts and Kuiper belt analogues, perhaps being detected by inhabitants of those systems if such inhabitants exist and possess telescopes and automated surveys, or perhaps passing unobserved, as most interstellar objects do, visible only in principle, in practice too small and distant and fast-moving to catch the attention of whatever eyes or sensors might be watching. The galaxy is full of such passages, a continuous exchange of material between systems, a slow mixing operating over galactic timescales. 3 Atlas joins the darkness gradually. The sunlight illuminating its surface weakens as distance increases, temperatures dropping from the already frigid 100 Kelvin reached during solar approach back toward the interstellar ambient of 3 Kelvin, cold enough that molecular motion nearly ceases, that thermal radiation becomes negligible, that nothing changes except through quantum effects and cosmic ray impacts. Processes operating on timescales longer than the current age of the universe. The object becomes isothermal with its environment, indistinguishable thermally from the cosmic microwave background. The relic radiation from the Big Bang that fills all space with a faint glow at 3 degrees above absolute zero. The rotation continues. The tumbling that began millions of years ago continues now, will continue for millions or billions of years more. The angular momentum conserved in the absence of external torques, the object spinning with the same 16-hour period, end over end, presenting its long axis and short axis to the void in regular succession. Though there is no sun to illuminate it, no observer to measure the brightness variations, no significance to the rotation, except as a historical fact, a relic of ancient dynamics frozen into the object's motion. Only took vacuum and cold to preserve everything. In interstellar space, erosion is negligible. No atmosphere to create drag, no water to cause weathering, no biology to break down materials, barely any dust to sandblast surfaces. The object will remain essentially unchanged for timescales approaching the age of the galaxy, its surface and structure preserved as they were when it left its home system. A time capsule drifting through space, carrying information about conditions billions of years ago or millions of years ago, depending on when it formed and when it was ejected. Information that will never be read, never be decoded, never be understood because no instrument will ever approach close enough to analyze it. The stars ahead shift imperceptibly in their positions as the object approaches and then passes them. Stellar parallax operating on interstellar baselines, though the shifts are measured in microarc seconds, far too small for any observer on Earth to measure even if they were still tracking 3i Atlas, which they are not. The object moves through, changing stellar configurations, constellations rearranging over millennia as stars follow their individual orbits around the galaxy. But to the object there is no change, no awareness of motion, no experience of journey, only the mathematical fact of position changing with time according to geodesics and curved space-time. The mystery of its shape will remain unsolved. Likely, whether it is a collisional fragment or a tidal remnant or a primordial form, whether its interior is solid or porous, whether it contains ice or has lost all volatiles, whether it could have become a spectacular comet. If its trajectory had brought it closer to the Sun, these questions have no definitive answers, only probabilities and plausible scenarios, the kind of ambiguity that characterizes most astronomical objects observed only remotely, at great distance, for brief periods. The universe is filled with such mysteries, most of them forever inaccessible to detailed study, known only through the sparse information carried by photons that happen to scatter in the direction of an observer who happens to be watching at the right time with the right instruments. Only took light to connect 3i Atlas to human awareness, photons travelling 8 light minutes from the Sun to the object, reflecting, travelling 8 hours or 16 hours or days from the object to Earth, entering telescopes, striking detectors, being converted to numbers that were analysed and discussed and archived. That connection is broken now. No new photons are being collected. The object fades from memory as it fades from view. Other discoveries claiming attention, other objects proving brighter or stranger or more accessible. 3i Atlas becomes a catalogue entry, a footnote in the history of interstellar object detection, one among what will eventually be hundreds or thousands, important for being among the first but not unique, not special, except in the ways all objects are special when examined closely enough, when their individual histories and properties are considered rather than their statistical role in some larger population. The silence is complete now. No signals from the object, no reflected light reaching Earth, no gravitational effects on anything nearby, no trace of its passage except the archived observations and the scientific papers that will cite them. The trajectory calculations that predict where it will be, though no one will ever check. The unanswered questions that motivated the observations but could not be resolved with available data. It continues into the dark, into the slow centuries and millennia of interstellar transit, into the deep future where its path may bring it near other stars, other planets, other systems that will be as unaware of its passage as the object itself is unaware of them. The galaxy, vast and empty and filled with such wanderers, ancient debris from ancient systems, drifting through space in a vast, slow dispersion that mixes materials across light years, that connects stellar systems through the exchange of fragments too small to notice but too numerous to count. The object moves through darkness now, through spaces between spaces, through volumes of the galaxy where starlight is faint and diffuse, where the nearest star is years away at light speed, decades away at the velocity 3 Atlas possesses. The tumbling continues in silence. End over end, the elongated form rotates through orientations no eye will see, presenting its long axis to emptiness, its short axis to void, the 16-hour period maintained by angular momentum that has nowhere to go, nothing to transfer to, the rotation as eternal as motion itself in the absence of friction. Time becomes meaningless at these scales. 1,000,000 years, 10 million, 100 million, the distinctions blur into a single continuous present, the object unchanged, the environment unchanged, only position shifting imperceptibly through coordinate systems that exist as human constructs, but have no physical reality in the emptiness between stars. The galaxy rotates slowly around its center. Stars drift in their orbits. Molecular clouds collapse and form new stars. Old stars exhaust their fuel and fade. And through all of this, 3i Atlas continues, a mote of stone and ice, perhaps, or rock alone, or some mixture known only to itself, carrying its composition and history forward into futures that stretch beyond imagination. The cold is absolute now. 3 Kelvin, the temperature of the cosmic microwave background, thermal equilibrium with the universe itself. Nothing sublimates, nothing changes. The surface, whatever its composition, is frozen into permanence, stable against everything except the slow sandpaper of cosmic rays and the rarest of dust grain impacts. Processes so slow they might add a single layer of atoms over millions of years, undetectable, insignificant, the object essentially unchanging for longer than stars live. Somewhere ahead, perhaps, another star. Somewhere in the object's future trajectory lies an encounter with another stellar system, another sun with planets, another opportunity for observational gravitational deflection or capture, though the probabilities favour passage at great distance, a miss measured in light years rather than astronomical units, close only by galactic standards, far by any measure that might allow detection or interaction. The object will pass through these systems as it passed through ours, silent, unannounced, unconcerned with whether it is seen or understood, obeying only gravity and inertia, the simplest laws, the oldest laws, the mathematics of motion that governed its path before biology arose anywhere, that will govern it after the last star fades. The universe expands slowly around it. Distant galaxies recede as space itself stretches, the expansion carrying them away faster than light could ever reach them, creating horizons beyond which nothing can be known or observed or visited regardless of technology or time. But 3i Atlas is too close, bound by gravity to the Milky Way, orbiting the galactic center with the sun and all nearby stars, part of a gravitationally bound structure that resists expansion, that maintains its integrity while the larger universe spreads thin and cold. The object will remain within the galaxy, its wandering confined to volumes measured in tens of thousands of light years, enormous by human standards, negligible compared to the observable universe, a local motion in a local neighborhood of space. The rotation slows by amounts too small to measure over millions of years, angular momentum gradually transferring to the quantum foam of space-time itself through mechanisms so subtle they barely exist outside of theoretical physics, effects that operate on timescales comparable to the evaporation of black holes through Hawking radiation, irrelevant for any practical consideration, mentioned only to acknowledge that nothing is truly eternal, that even rotation eventually decays given enough time, given universes old enough and cold enough and empty enough that such processes can complete. But for now, for the next billion years, for timescales longer than Earth has hosted complex life, 3 Atlas continues tumbling, continues moving, continues existing in the silence and darkness between stars, a traveller without destination, a fragment without purpose, a piece of one planetary system's history drifting through the galaxy, joining the countless others that make the same journey, together comprising a population larger than all the planets and asteroids and comets still bound to stars. A vast invisible sea of debris that fills the galaxy, unseen, mostly unknown, but there, always there, moving through the dark. And in that darkness, nothing changes. The object rests in its motion, still in its tumbling, silent in its passage through the endless night. Time moves forward. The object continues. The stars wheel slowly overhead in patterns that shift over millennia, and somewhere, perhaps, in some distant future, another telescope will catch its light. Another civilization will mark its passage. Another brief moment of observation before it fades again into the eternal dark from which it came and to which it returns, now and always, without end.